So as waves travel through different mediums, or you send them through a layer that has more than one medium consecutively, then they can bend instead of reflect. And so when the wave bends, or wave's direction changes, that occurs when the wave enters a different medium at an angle, we call that a refracted wave as opposed to a reflected wave. And so let's say from our source here we have an incident ray that goes into the normal, and let me draw that more properly, at this angle. A reflective wave would look like this. Okay, and this would be reflection. And we know that these two angles would be identical. However, the refracted wave, let's assume that the layer up top is the medium of air. And then over here is water. These are two different mediums with two different reflective indexes. So what's going to happen is, if you shine your light ray, this thing over here, directly into the water, then instead of being reflected, your water is going to bend it downwards at a different angle. And it would probably be a bit more noticeable, so it would be something like this. And so this would be our refracted ray. And the angle of refraction would be this, and that would not be the same as your reflection. Now, the ability of a medium to refract light or to bend light as it's coming in is calculated with something called the Index of Refraction. And what that is that's N is equal to C over V. Your N is your index of refraction. And every material is going to have a different index of refraction, or refractive index. And it's calculated from the speed of light, which is always going to be constant. That's going to be 3.0 times 10 to the 8 meters per second. So speed of light divided by the speed of the light when it travels through a medium. So this is speed of light. We could even, I'll get a bit more specific at the top over here. This is speed of light in a vacuum, so we're assuming no frictional interference. And this would be speed of light when in the medium. And so they compare the two speeds, and what you basically get is a ratio of how much the medium slows the light down. And so, keeping the idea of the fact that every material has its own refractive index, or its own N value, a Danish physicist and mathematician by the name of, his nickname was Snellius, but we call him as Dr. Snell, he came up with the following relation that would attempt to bridge the refractive indexes of two different mediums as a light ray passes through. This relation is referred to as Snell's law, whereby the refractive index of the first medium multiplied by the sine of the angle of incidence through the first medium is equal to the refractive index of the second medium multiplied by the sine ratio of the angle of refraction of the second medium. Our first refraction example reads as follows. A 5.0 Hertz water wave traveling at 0.31 meters per second in deep water enters shallow water. So there's a change in medium here, or change in depth. The angle between the incident wave front in the deep water and the boundary between the deep and shallow regions is 50 degrees. The speed of the wave in shallow water is 27 centimeters per second. So what we're going to do is we're going to calculate, just convert that quickly to 0.27 meters per second. Find the angle of refraction in shallow water. And then B, find the wavelength in shallow water. Now we're going to combine a couple of equations here in order to isolate and solve for what it is that we're trying to look for. We know that Snell's law is N1 sine theta I equal to N2 sine theta refraction. If we were to place all the like terms together, we could get this ratio, which is sine theta I over sine theta refraction, which is equal to our N, we could even say our second medium refractive index over our first medium refractive index. Now if we go back to a previous question, remember that V1 over V2 is equal to N1 over N2. Sorry, let me backtrack. From previous physics classes, we can remember, and this is back in grade 10, that your sine theta of incidence is equal to your wave of the first boundary, and sine theta refraction is equal to the wave of the second boundary. And we can generalize it to this, which means that from these two here, we can generalize that N2 over N1 is equal to the lambda of the first medium over the lambda of the second medium. And if we can assume that the lambda first medium over the lambda second medium is equal to N2 over N1, then we can also say that it is equal to V2 over V1. And so when we rewrite our equation here, we're going to go sine theta I is equal to V2 over sine theta refraction is equal to or V1. And so this is the governing equation that we're going to use to solve for this problem. Now in the end, what we're trying to do is get the angle of refraction. So we're going to isolate for this angle over here. And I do that by simply just cross multiplying each, and then I'm going to divide both sides by the V2. And then taking the sine inverse of that will give me my angle of refraction. And so when I plug that in, I have my theta of incidence, which is 50 degrees as outlined by the question, multiplied by the initial speed was 0.27 meters per second. And then I'm going to divide that by about 0.331 meters per second. And when I plug that in, I end up getting an angle of refraction of about 42 degrees. And that solves for part A. Now for part B. What we want for part B is the wavelength in shallow water, which is the lambda over here. And remember when I said that this relation is going to come into handy? That is simply because we're going to use it in order to get this value here. Now, if we wanted to use this equation here, which is N2 over N1 equals lambda 1 over lambda 2. We could use that, but the problem is we don't really have any of the reflective indexes at this point, and so we're going to have to find our wavelength in shallow water using another mean. Now, there are several formulas that we could use. we are given a frequency. We have a frequency of 5.0 hertz. Okay, and that's the frequency of the water wave. So that wave is going to be applied to both the deep ends and the shallow ends. So what we're going to do is, since we have the frequency there, and as well we have the speed that the shallow wave is going at, which is 27 centimeters per second, we can just use the universal wave equation that we stated in the first video in order to solve for our final wavelength here. And so we're going to convert this to meters per second, which is 0.27 meters per second. The frequency is 5 hertz. And we're trying to get our lambda of the shallow wave. When we plug in our numbers and divide both sides by the frequency, we end up isolating for our hertz, for our wavelength, and that ends up being, if we convert it to centimeters, about 5.4 centimeters. Alright, our second example reads, a light ray travels from glass into water. Find the angle of refraction in water if the angle of incidence of the glass is 30 degrees. Find the speed of light in water. The indexes of refraction are 1.5 for glass and 1.33 for water. So what we're going to do here is we're going to say that the index for the glass is going to be N1, and that'll be 1.5. And then, of course, for the water, we're going to label that as N2, and that's 1.33. Let me just make that a little bit neater here. Sorry, guys. The angle of incidence of the glass is going to be our EI, which is given to us as 30.0 degrees. And of course the refracted angle, well, that's what we don't know. So the first part of this question is going to be relatively simple. Using Snell's law, we can simply isolate for the angle of refraction. So that would be N1 multiplied by sine theta I is equal to N2 multiplied by sine theta refraction. And then dividing both sides by the index of refraction for water, we end up getting this as our final equation. All right. So now, what we end up doing is we're going to just plug in our values and see what we get here. 1.5 for our index of refraction for water. The angle of incidence was 30 degrees. And of course, sorry, 1.5 is not for water, it's for glass. Of course, for water, it's 1.33. And then when we plug that in, we get sine of refraction. And then we're going to take a sine inverse of this whole thing here. So sine inverse, because that's actually going to give us the angle of refraction. So sine inverse, which is 1.5. And then we end up getting about 34.3 degrees as our refraction angle for water, or in water. Now for part B of the water, we don't really have a speed in glass to compare it to. We do have a speed in the air though. So what we're going to do is, using our tables, we're going to look for the refractive index of air, and we'll label that as N1. So this will be for air. And when you look at your table, it has an index of 1. And then of course the water, which we used previously, is going to be 1.33 repeat. Now, we do have the speed of light in air, which is 3.00 times 10 to the 8 meters per second. But we know that refraction is essentially caused by a change in speed of the wave, so we don't really know what the speed of light in water is, but we can isolate for it using an equation that we did list previously and that was given to you in grade 10 optics. And that would be the speed of light in the air divided by the speed of light in the water is equal to the refractive index in water divided by the refractive index in air. And of course, cross multiplying and then flipping, we can isolate for our speed of light in water. And so this becomes our working equation that we use to solve for this. And once we have all these values, we can just plug it in as follows. And when we calculate this, you should get a speed of about 2.26 times 10 to the 8 meters per second. And so the relationship that I want you to see here is, you can see that it actually slows down a little bit. And so as your refractive index increases, so we're going to write as the refractive index, which are your n values, increases, your speed, and that'll be wave speed, actually your speed of the wave would decrease. Your water had a greater refractive index than the air, and so its speed was less than the air, which had a smaller refractive index. Now, depending on the angle of the incident ray, you can get what is called a total internal reflection. Now, as you change mediums, which means that you change speeds, there is going to be refraction. And the refraction angle, and I'm going to say this right here, your refraction angle, in almost all cases where you're going from a slower medium to a faster medium, is going to be bigger than your angle of incidence. Okay, and this would be the slower medium to the faster medium. So there are times where instead of getting refracted, your incident ray might get completely reflected back into the first medium. And when that happens, we say that it experiences total internal reflection. Now, for that to actually happen, you typically require two things. One is that the light ray, that is the source of the incident ray, is going from the denser medium and approaching the less dense medium, or the slower medium to the faster medium. And the second condition that would typically cause your total internal reflection would be that the angle of incidence is greater than the critical angle. Now, just what does that mean exactly? Well, we'll show you right below. Let's say that below the line here represents the slower medium, or the denser medium. Okay, so we're going to write slower medium, right, or you could say denser. And then everything above the black line is the faster medium. Okay, so for the first thing to be true, the first condition to be satisfied, light can't travel like this from the faster medium towards the slower. It has to be the opposite. So it's got to go from the slower medium and approaching the faster medium, which is above the black line over here. Now, when that happens, and we create our normal line over here, you would get a line going through it like this, and this here would be your angle of refraction, right? The amount that light had actually bent here. This would be your angle of incidence. And so what we're trying to figure out in this case is there ever a condition where you won't have any angle of incidence, angle of refraction, and you would have just complete total internal reflection, and it would go back into the medium? And the answer is yes. However, in most cases, what we actually try to do is approach a refraction angle of 90 degrees. And so is there an angle that we can actually have up to 90 degrees refraction all the way up to here? The angle that we would have to induce with the incident ray that would cause a 90-degree angle would be called the critical angle. And so we're going to write theta critical, and what this is this is the angle of incidence that would cause 90 degrees of refraction. And so this would be the critical angle stated here, and that would cause 90 degrees of refraction. If this angle is exceeded, then the light is actually going to reflect back into the denser medium, and you would have total internal reflection. Now, one thing I'm going to correct is that I realized that I kind of drew it, the refraction angle going upwards. But if the refraction angle, remember, it's actually read like this. This is your index of refraction. And so, and I'm going to erase this here. In 90 degrees of refraction is going to actually be read this way. And so we don't want the line, if we don't want light to escape, we don't want our light ray, the incident ray over here, to go past this portion over here. And that's because we're reading it like this. So we don't want it to go past this. If it does go past, well, then that would just be a reflection. So what's the critical angle that we can't exceed so that you form 90 degrees of refraction between the water and the less dense surface at the top over here? So in an example to show you how this works, what is the critical angle of an incident ray traveling from glass, which has an index of refraction of 1.5, to water, 1.3. So let's pretend that there's a sheet of glass, and then above it here, okay, we'll just kind of do it like this. This is water. And so we have an incident ray here that's going through glass. It could be opaque glass, maybe that's why it refracts a lot more. Here's the incident ray. And remember that in order for total internal reflection to not occur, we can't exceed a refraction angle, read, of course, clockwise, of 90 degrees here. And so using Snell's law, we can easily isolate for this critical angle over here, which is, you can think about it as the maximum incident angle. This will be of glass, and this side, sorry, we should have put N2. This side will refer to the water. And so what we're going to do is we're going to isolate for side theta here, which, dividing both sides by the refractive index of glass, will give you that. And then, of course, to get theta, we're going to sine inverse this entire ratio here. Once we do this, we just plug in the values in our calculator as follows. And so this would give us a critical angle of 62.7 degrees. And what that means is if we exceed this value, your light ray is going to completely bounce back into the medium. And so its Phyto Diagram, right, would look like this. If the top portion is the water and the bottom portion is the glass, if we have, let's say, 65 degrees, so let's say it's at 65, then your ray would simply go like this. And it would not escape at all to the surface, right, to the water wave. So this would be total internal reflection. But there is a way to keep all the light from escaping, and that's just to simply, reach the critical angle at 62.7. And that would be just as effective at keeping all the light energy into the first medium and away from the second.